Motion analysis.
Learning objectives.
At the end of this topic, you will be able to understand the representation of orientation of a body in matrix form, analyze the concept of transformation of a point from one frame to another frame, discuss the effect of rotation of a point about fixed frame and current frame, explain the homogeneous transformation matrix and evaluation of its inverse. Outcomes.
By the end of this topic, you will be able to
understand the different types of transformation, derive the rotational matrices for rotations about various axes, understand the concept of homogeneous transformation matrix, solve problems related to composite transformations. Homogeneous transformation. Homogeneous transformation matrix helps introducing the position vector in the orientation matrix 3 cross 3 by augmenting it to make it a 4 cross 4 matrix. A transformation matrix must be in square form. It is much easier to calculate the inverse of square matrices. Geometric interpretation of the homogeneous transformation is given here. A pure translation in 3D homogeneous form. Consider the translation of dx, dy and dz about x, y and z axis respectively, which can be represented by the matrix. Inverse homogeneous transformation matrix. Inverse of the rotation submatrix is equivalent to its transpose. A point P in space. 3 coordinates relative to a reference frame. A vector P in space. 3 coordinates of its tail and of its head with W as a scaling factor. Here, x is equal to ax star w, y is equal to by star w, etc. Description of a position. The position point of a vector is defined along the vectors xa, ya, za. Often, a point is not enough. It needs orientation. The matrix of the position vector is shown here. Motion analysis. Homogeneous transformations. Representation of transformations. A transformation is defined as making a movement in space. It can also be defined as mapping a point from one frame to another. A pure translation, a pure rotation about an axis, a combination of translation or rotations. Example for 2D rotation is shown here. Mark the points x0 and y0 along the vector xa and ya. The vector xb and yb is drawn along the degree theta. Point x1 and y1 are marked in the vector xb and yb. Basic rotation matrix. Consider a point P with coordinates px, py and pz with respect to the x, y, z frame. Let the unit normal vectors along these axes be ix, jy and kz respectively. The same point P with coordinates pu, py and pw can also be expressed in another frame ouvw, which is rotated by an angle alpha. The corresponding unit vectors along these axes are iu, jv and kw respectively. P, xyz is given by, if we consider o, x, y, z as frame 0 and ouvw as frame 1, then the above equation can be written as R10 is a matrix whose column vectors are the coordinates of the unit vectors along the axis of frame 1, expressed relative to frame 0. The point P can also be expressed in the frame 1, which is given by, as dot product is commutative from the above two equations, it can be concluded that the matrix R is referred to as orthogonal matrix as its transpose and inverse are identical. When this matrix contains unit vectors, then it's termed as orthonormal matrix. R represents the direction cosines matrix and it's also known as the rotation matrix. It is in general a 3 cross 3 matrix for pure orientation and hence it has 9 elements which represent the orientation of a body in space. These 9 elements are not independent as we know that some constraint equations exist. Robot reference planes. World reference frame, which is also known as universal coordinate frame, is defined by the fixed xyz axis. The joints of the robot move simultaneously so as to create motion along the 3 major axes. Joint reference frame is used to specify movements of each individual joint of the robot. In this case, each joint may be accessed individually, hence only one joint moves at a time. Tool. Hand reference frame specifies the movements of the robot's hand relative to the frame attached to the hand. The X-Y-Z- axis attached to the hand define the motions of the hand relative to this local frame. All joints of the robot move simultaneously. N is normal vector, S is sliding vector, A is approach vector, normal to the tool mounting plate. Basic rotation matrix. Rotation about x-axis by angle theta is given by. Rotation about y-axis by angle theta is given by. Rotation about z-axis by angle theta is given by. Alternate method. Alternate method for finding the rotation about the axis is given here. Example problem is given here. Find the composite rotation matrix for the following sequence of operations. Rotation alpha about x-axis, rotation theta about fixed z-axis, rotation phi about fixed y-axis. Rotation r is given by. Matrix representation. Representation of a frame at the origin of a fixed reference frame. Each unit vector is mutually perpendicular, normal n bar, orientation or sliding, O bar or S bar, approach vector A bar. Representation of a frame in a fixed reference frame. Each unit vector is mutually perpendicular, normal orientation, approach vector. Representation of a rigid body. An object can be represented in space by attaching a frame to it and representing the frame in space. Constraints equation. Linear constraint equation provides a more general means of relating degree of freedom values than is possible with simple coupling. Consider the matrix. The orthogonal vector conditions and the unit vector conditions for the matrix is shown below. For rotation about x-axis by an angle alpha, the rotation matrix is calculated as rotation x, alpha is given by. Similarly, we can write effect of rotation about fixed frame. Effect of order of rotations of a cuboid about the principal axis of a fixed frame are shown here. Effect of rotation about moving or current frame. Effect of order of rotation of a cuboid about axis of the moving frame.